guys, welcome to my lecture on communication system. So in this lecture we are going to start a topic on digital communication, which is signal space representation of waveform. This topic is not at all related to my previous lecture, but you can watch my previous lecture also. The link is in the description below. So let's get started toward it. Okay. So what we will learn in this lecture is that any set of signal is equivalent to a set of vector. Signal has the basic properties of vector, and that we will going to learn is we will determine an equivalent set of vector for a set of signal and introduce notion of signal space. So sometimes signal space representation is also termed as signal constellation. Okay, signal space representation is equal to signal constellation diagram also. Okay, so what these 3 points means, I will sum up in a single formula and you will get the feel of it. Okay, so the formula goes like this, that is V is equal to so in this case, what is V? V is our vector. What is EI? EI is nothing but orthogonal basis, and this is projection of vector V on unit vector EI. Okay, so this lecture is very important for digital communication, so I will explain this formula also for you. So what is going on in this formula is that we have some vector, like say that is 3i plus 2j plus something 2k. Okay, like this. So this is I, okay, this is j, and this is k. So in this case, I, j and k are my orthogonal vector. Okay, because they are perpendicular to each other, and that is I dot j is equal to 0, I dot k is equal to 0, meanwhile j dot k is also equal to 0. Now see, what is Vi in this case? That is, if we take the case that V with dot product I will give me Vi. Okay, so what it is, that is 3i plus 2j plus 2k multiply by I will give projection of this vector on this orthogonal basis, that is here it is 3. Okay, so in this lecture what we are going to learn is that we will be given some signals. Likewise, we been given 3 signals, and we are going to form this orthogonal basis. First we are going to find this orthogonal basis and represent our signal in the form of vectors like this. Okay, so this is the theme of our lecture. Okay, so let's get started toward it, and I will try to explain you as much as simple as I can. Okay, so what is our theme is that we are first going to find out the orthogonal basis of these signals and represent our signal in this signal space representation diagram. Okay, so before I move to some important topic, I just want to explain you some terminology. So what is row vector and what is column vector? A row vector is nothing but in this case we have our orthogonal basis as I, j and k, so it is represented as row vector as 3, 2, 2, and in terms of column vector it is nothing but it is represented as 3, 2 and 2. Okay, so now the second terminology is inner product. So what is inner product is that it is nothing but v1 dot v2. That is nothing but equal to v1 dot v2, which is equal to I equal to 1 to n v1i and v2i, which is also equal to v2 Hermitian v1. Okay, so what does it mean? So we have our v1 as n-dimensional vector, that is v1 vi1, okay, v12 and up to v1 of n. Okay, here it is v11, v12 and up to v1 of n transpose. So this is our column vector. Okay, what does this Hermitian mean is that now see what is v2 is nothing but v21, v22 up to v2n transpose. This is also column vector. So we need to find the dot product between these two. So what we will do Hermitian of this v2 vector. Now what is Hermitian means is that first we will transpose the matrix, transpose our vector, and then we will conjugate its element, conjugate the element. Okay, so this is our column vector. So it will look something like this. And then what I will do the transpose. So it will become row vector v1, v22 and up to v2 of n. Then what I will do the conjugate of this v21 like this. So my inner product will look something like this. That is v1 dot v2 will look something like this. That is v2 Hermitian v1. So it is nothing but v21 conjugate v22 conjugate and v2n conjugate, and then v11 v12 likewise v1 of n. So in the end it will look something like this. That is v21 conjugate multiplied with v11 plus v22 conjugate multiplied with v12 and goes on, and in the end it is v2n conjugate multiplied with v1 of n. So this is my inner product. And the next terminology is our norm. So I will write norm. Norm is nothing but it is the inner product with itself. So it is represented like this. So it is nothing but this, which is represented as and here is that there is 1 by 2 also. So we need to find the root of this also. So it is represented as since v Hermitian into v will become mod of v, okay, and we will take its half. Okay, so it is represented something like this. Okay, I hope you get this. First we have learned that it is a row vector, then column vector, then we find out what is inner product, then we find out that norm is nothing but the product of two vector which is same. Okay, in this case it is v dot v. It is represented something like this. Okay, so there is a procedure to find out the orthogonal basis, which is Gram-Schmidt procedure. So let's get started toward it. So we need to find the orthogonal basis for these vector, that is v1, v2 and v3. As we have studied vector, we know that the orthogonal basis is I, j and k, but in case of a signal space concepts, we can't found it by our intuition. So how we can find out? So let's get started. So we have given v1. So to find the first orthogonal basis, what we have to do is we have to do we have to put our vector v1 and find the norm of our vector v1. Okay, so this is v1 is equal to 3i and mod of v1. Okay, norm of v1, sorry. So what is norm of v1 is nothing but v1 dot product with v1 inner product with itself. So it will be 3 into 3 half. Okay, this is my norm of v1. Okay, so it was nothing but equal to 3. Okay, so it is I. So the first orthogonal basis in this one is I. Okay, so how I found the norm is nothing but the length of this vector, which is nothing but 3. Okay, so here I had done 3 into 3 is equal to 9 and 9 root is equal to 3. Okay, now we need to find the u2, that is our second orthogonal basis. So what we need to do here is that first we will find u2 dash, which is nothing but vector v2 subtract with projection of vector v2 on our first orthogonal basis, that is u1, and multiply with the orthogonal basis. So here in this case it will give us the length of our projection on u1. And multiply with u1, so it will give us u2 dash. So in this case, so what it will come out, so what is our v2 is here in this case is 3i plus 2j. So 3i plus 2j dotted with, I mean a dot product with u1. u1 is nothing but I into I. So what it will give me here is, that is, this is nothing but give me 3. Okay, and 3 into I. So this and this will cancel, which is u2 dash is nothing but 2j. Okay, now what is u2 is u2 dash upon norm of u2, that is length of this vector u2 dash. So it is nothing but 2j upon 2, which is nothing but j. Now likewise we need to find u3. So first we will do u3 and take the norm of this. So what is u3 dash is nothing but u3 minus, sorry, it is v3 minus v3 into u1 . Okay, so what we are doing here is that we are subtracting the projection of vector v3 on u1 and projection of vector v3 on u2. Here it is u2. Okay, so what it will look like is nothing but, what is our v3 here is 3i plus 2j plus 2k. Okay, then I will multiply with I, then I, then here it is same dot product with j and j. So it will turn out here is at here it is v3 minus. Okay, so what is 3i plus 2j plus 2k and here it will turn out to be 3i, and here it will turn out to be 2j. So it is nothing but left with 2k. So u3 is nothing but u3 dash upon norm of this. So we have found out our orthogonal orthogonal basis from this Gram-Schmidt procedure. So how we can represent our vector in orthogonal basis function, which is I, j and k in this case. So I had drawn a simulation for this. So I will show you here. So the arrow represented here is I. So this is my I, this is my j, and this is my k. Okay. So this is my 3i. Okay, that is v1, and this is my vector v2, the second dot here, and this is my vector v3. Okay, so this is 3 unit length, so this is 3i, and here you can see that here it is 3i plus 2j. So this is my second vector, and this is my last vector, that is 3i plus 2j plus 2k. So this is vector v3, and this arrow represented my orthogonal basis, that is I, j and k. I hope you are enjoying my lecture, and if you are enjoying my lecture, then please like and subscribe to my channel. So in the next lecture we are going to learn about how we can represent our signals also in terms of these orthogonal basis and draw the signal in terms of vector. Okay, keep learning and goodbye.